we were discussing infinite sets, the interesting part of infinite sets is that it actually differentiates between intuition and logic in a perfect way. For example, when you are in finite zone, often the logic and intuition go hand in hand. So what you intuitively think of, you will see that that is applied in practice. It is also logically making sense. But when it comes to infinite sets, you see a clear gap between intuition and logic. For example, when we were looking at the countability arguments and trying to show that there exists a bijection between integers and the natural numbers, the intuition kind of says the set of integers is at least 2 times n. So we think that integer set is a bigger set compared to the natural numbers. But logic says there exists a bijection between natural numbers and the integers. Therefore, the cardinality of n and I are one and the same. And so this is something one has to make a note of it. And there are many such things. So intuition will tell you that both infinite sets are of different cardinality, but logic will tell you there exists a bijection, and due to which you can conclude both are having same cardinality. So like this, we come across many interesting sets in computer science when we start looking at algorithms and the number of inputs to the algorithm and so on. So one has to pay attention to when you talk about the countability part, whether the underlying set is countable or uncountable and so on. I'll give you a couple of case studies. The more on this we will see as we move along when we start looking at subsequent courses like design and analysis of algorithms, automata theory and so on. So a couple of remarks. So if we establish a bijection between n and A is some set, then you can conclude, so conclusion is A is countably infinite. For that matter, I can take any countably infinite set. So any countably infinite set, bijection with A, you can conclude that A is countably infinite. On the similar line, you establish a bijection between R and A could be some set, you can conclude that A is uncountable. Not just this, you can take any uncountable set. So any uncountable set, bijection with A, you can conclude A is uncountable. So I can take the real line 3, 4, I can take 0, 1. In fact, the open interval 0, 1, they are all uncountable. So one can establish a bijection with any of them and establish this result. Okay, and if you look at an uncountable set, the uncountable set contains, for example, look at R. So R contains, you see that 0, 1 is a subset of this, and R also has I in it. So any uncountable set, if you see, it contains an uncountable, a non-trivial uncountable set as a subset. Similarly, it also contains a countably infinite set as a subset. Okay, and it goes, this is true with respect to, of course, it also contains a finite set. That's understood. It also contains a finite set as a subset. In the context of infinite set, you see that it also contains another uncountably infinite set as a subset. So please make a note of this. Now we will see a couple of interesting stuff which are related to this. Let's look at say sorting problem. So input as an integer array, say of size n, which means n is part of the input. Very important. N, the input size n is part of the input. Now question is sort the array of size n. Now what is that we are interested in is the following. How many different n sized, it's an integer array, how many different n sized integer arrays are there? So from the countability perspective, we are interested in this. It's like this, and you are asked to write an algorithm, subsequently an implementation using say C++. Now that you have written in C++, we want to test whether your program is doing the intended task. Now naturally you start supplying one test case after another test case. Now it is natural to ask how many different test cases are there for this problem. That's all. From discrete math perspective, we are going to count. From algorithm perspective, you start supplying and verifying whether the algorithm is indeed working or not. Now it is n sized array, which means n is fixed. It's very important to understand this. N is fixed, meaning integer array of size, meaning size n, meaning n is say 5, n is 10. So you start supplying all possible 10 sized arrays. So n is fixed. For example, n is say 10, and which means input will be all possible 10 sized arrays. Now we are asking how many different 10 sized arrays are there. See, please note my first input will be like 1, -1, 4, 6, 7, 9, 10, something like that. So there will be 10 numbers. Now there will be no 10 numbers. Then you supply I2 another some integer. So 1, -5, -6, 7, 100, 10 power 10, and so on. Again another 10. So you keep supplying one input after another, and the cardinality of each input is 10. Number of this thing, the vector size is precisely 10. Now we are asking how many different 10 sized arrays are there. So in general, if you look at the input has got A1, A2, so on up to A10, and each AI belongs to I. Now what is that we are asking? How many different 10 sized arrays are there? So please note A1 belongs to I. So all possible values for this, and A2 belongs to I, and A3 belongs to I, so on up to this, which means each input you can see it as a vector. Where do they come from? They actually come from the cross product I cross I cross I cross I 10 times. The input is a vector, and it's an element in this. So 1 belongs to I, and 1 comma -1 belongs to I square or I cross I, and 1 comma -1 comma 6 belongs to I cube or I cross I, and so on. So which means this input belongs to I cross I cross I 10 times. So that shows that listing all possible tensized arrays is equivalent to counting the size of this set, because every element over here corresponds to one input with respect to this problem. So which means what is the cardinality of this? And please note, we know I is countably infinite. Through snake tail argument, you can list I on this side and another I on this side. Then you take this one, then you go up and take this, come down. If you follow this argument, you can show that I square is countably infinite, because it has got a mapping to the set of natural numbers. Then you know I square is countably infinite, so you can list I square on one side and I on another side. Now each element over here will be something like 0, 0, 0, then 0, 0, 1 and so on. Now this space contains I cube, so which means from this you go up and then come down, all that you do. Now you see that I cube is countably infinite. Then keep I cube on one side, I on another side. You can see that I4 is like that. If you continue, you see that I power 10 is countably infinite. So if we continue this argument, you will have I power 9 on one side, and which we know through this argument countably infinite, I on the other side. Now this space will list all possible inputs of size 10. So which means the entire cross product of I power 10 is listed here, and which you can enumerate, thereby you get a bijection to n, which shows that I power 10 is countably infinite. And that tells you that number of possible inputs to 10 sized array, or this sorting problem of input size 10, is countably infinite. So, and this brings you a strong message. So when we implement algorithms as part of test cases, what we test is finitely many, and with that we conclude that the program is working fine. So we don't actually experiment all possible inputs, which is not possible, because all possible inputs are so much in number, which is countably infinite, and one cannot supply countably infinite inputs to any algorithm, and when it is implemented through some programming language, say C or C++. So that shows that what we experiment as part of engineering or software engineering test cases is only finitely many. So please remember that. Now you can vary n. Instead of sorting n of size 10, you can ask for 5, you can ask for 100. So the same argument works as long as n is fixed. Suppose n is a variable, we will see how to take this argument forward. So now I am modifying this question. So input is integer array. That's all. Question, sort the array A. Now if you look at this problem, this one and this one are different. In this it says integer array of size n. N is part of the input, which means n is fixed. So you say that you want to sort an array of size 10, and you start supplying all possible values for the array A. Now if you look at this problem, in this cardinality of A could be anything, because we have not specified anything about the size of A. So A could be anything. So it could be 1, it could be 2, it could be 3, and it could be any number. It can go all the way up to the natural number. So which means the size of A is not fixed, which means it is a variable. Now, listing all possible inputs is equivalent to saying list all inputs of size 1, of size 2, and so on up to of size the natural number. So we want to list all possible inputs of size 2, 3, 4 and so on, and the size can go all the way up to the cardinality of natural number. Okay, it could be 4, it could be 5, it could be 6 and all the way up to infinity. Now this is what we mean when n becomes a variable. We don't know because this question says a is arbitrary and it can take any values, correct? So now, which means we have to take all possible values for a1 and all possible values for a2 and so on up to all possible values for this one, and after that so which means you get something like this. So I've got a1, a2, so on up to ak, and if k is fixed, then you say k is something like say 5, 10 and so on. Now you say k is a variable, which means k belongs to n. K can even be n itself. So which means a1, a2, a3, a4. So you get to see I cross I, like that. We are doing this one, say k times if k is fixed. But the same thing, all this we do it this many times if k is, there is no k, in fact now k is a variable. Okay, so it could be 1, it could be 2, it could be anything, it could even be an infinite set, which means cardinality of a can become the cardinality of n. Now if that's the case, what would be our count? Okay, so please note, so we have shown that power set of n, we have shown that power set of sigma star is uncountable. Now using this one can show that power set of n is also uncountable. So otherwise you refer the scribe, you can see this. So this is uncountable. One can establish that power set of n is also uncountable. Fine. Now I am saying this one and the count when array size is a variable, they both are related. We will bring that connection. With that we see an interesting counting argument.